Well, good morning or good afternoon or whatever part of the day it is when you're watching this. Maybe good evening. Coming at you from the carport again because it's raining in Ellensburg, so that the rest of my yard is pretty much off limits today. Today's lecture material is the eruptive styles of volcanoes. We're picking up right where we left off from yesterday's stuff. And if you haven't watched yesterday's, which is magma chemistry, the chemistry of magmas, we really need that. We really need that information. We need that base of knowledge to talk about what we're going to talk about today. But man, this is the sexy stuff in geology. The volcanoes, earthquakes, the destructive stuff. That's what you know. The only time geologists are ever in the news is when something bad happens, and this is the stuff that they're in the news for. This is the stuff that people want to hear from geologists about. So volcanoes. We left off yesterday. Oh, check this out. I got a clipboard. I'm moving up in the world. We left off yesterday with this classification of magmas. We have our 6 main igneous rock types. And the big news from yesterday is that correlates with the amount of silica in the magma. 45% silica, that was our melted oceanic crust. And 75% silica, that was our melted continental crust. And 60% we decided that was our intermediate, when we have a mixture of melted continental and oceanic crust. So what we're going to do today is we're going to talk about, let me check my notes, make sure that I'm going in the right order here. We mentioned yesterday how we could go pack a picnic lunch and eat it right next to a river of orange lava pouring out of Hawaii, pouring out of Kilauea on Hawaii, and that it's a relatively safe volcano. It doesn't explode. Lava runs right out of it. It's low viscosity. That was another big word for yesterday, was viscosity. And you can go from our continuous, more or less continuous eruption. It can erupt for months at a time. In Hawaii, you can go to Mount St. Helens, and now we don't have rivers of orange lava. Instead, we have big clouds of ash miles up into the air. And then we can go even bigger and scarier than that. And we can go to Yellowstone, super volcano, where massive explosion creates a huge crater in the earth. And fortunately for us as a species, I suppose, humans have never really been around to see one of these supervolcano eruptions. The last time Yellowstone erupted was 640,000 years ago. But anyways, let's start with our mafic. That's our 45% silica lava. And so yesterday we talked about the chemistry of the lava, or the magma, and today we're going to talk about the mountains, or the actual volcanoes that are formed as a result. So what we're going to do, we're going to make 3 sort of cartoons of what's happening here. We're going to make 3 cartoons. And so we're going to draw in our notes. Leave yourself plenty of room, because we're going to have some pictures, maybe even a page for each one. I don't care. We're going to draw in our notes. We're going to draw some flat ground, and we're going to draw sort of a cartoonish magma chamber below that flat ground. We're in cross section, and we've got this cartoonish magma chamber. We're imagining it just a big room full of magma, big room full of molten crust. And we're going to start with our mafic magma, 45% silica. Cool. So what we want to imagine here is somewhere, so there's a bunch of magma down in here, and it's melted, and it's getting ready to erupt. Something is going to cause our magma to erupt. And so it kind of swirling around, and as our magma erupts, I'm going to try to draw this upside down, and we'll see how it works. As our magma erupts, it's going to come up, and it just flows out to the sides. More magma comes up, and it flows to the side, flows to the side. More magma comes up, flow. We've got rivers of orange lava coming up and flowing, and this can happen for months and years and thousands of years and millions of years until we build ourselves a mountain. All right, you see what we're doing here? We have, that wasn't half bad. We have flow in both directions away from that vent, away from that fissure, away from that crack in the ground where that magma is coming out. Now it's lava. And what we end up with is this sort of wide, rounded shape. And there's a word for this kind of volcano, and the name that we give this kind of volcano is a shield volcano. Shield volcano. Can you picture Captain America's round shield with a star on it? That's what we're talking about. We're talking about a wide sort of dome-shaped mountain. Our classic example here is Kilauea in EUEA in Hawaii, which Kilauea, in case you didn't know, is the biggest volcano, biggest mountain, in fact, on Earth. It's what? I thought Mount Everest. Mount Everest has a peak that is the highest above sea level. It is the tallest above sea level. But the tallest mountain on Earth from base to peak is Kilauea. It's only about 7,000 feet above sea level. But if you follow it all the way down to the ocean floor, you got to go 17,000 feet down to the ocean floor, which makes Kilauea 24,000 feet-ish from base to peak. Massive mountain. Massive mountain. So that's a shield volcano. Mafic magma. Why is it mafic magma? Because it's 45% silica. Why is it coming out and just running down the sides in our rivers of orange lava? Well, it's doing that because it doesn't explode. There's no explosions because it's low viscosity. Low viscosity, 45% oceanic crust. (45% low viscosity oceanic crust). Okay. So that's our shield volcano. Ocean floor, growing off the ocean floor. You don't really find shield volcanoes anywhere but coming off the ocean floor. There's a couple of exceptions to that rule, but we're gonna we'll hold on to those ideas for a little while. We're doing global patterns right now, just the general rules, and then we'll learn how we break the general rules. So, shield volcano. Let's move from the ocean to the coast. We're going to move east from Hawaii to the coast of of North America, or the coast of South America, if you like. Now we're going to talk about our intermediate volcanoes. Intermediate. What was our number for that? 60%. 60% silica. We're going to make the same drawing. Or we're going to start the drawing the same anyways. With flat ground, cross-section, magma chamber. Flat ground, cross-section, magma chamber. Well, what do we know about what do we know about 60% silica magma? It's intermediate because it's a mixture of melted continental crust and oceanic crust. We know that. And we know that it's medium viscosity. We're starting to get sticky. It doesn't just run. It has resistance to flow. So what's going to happen here? Well, here in our magma chamber, magma is going to swirl around, and eventually at some point, we're going to force our way up in here, and then something is going to happen that's going to cause this volcano to erupt. But it's not going to flow like our shield volcano, it's going to explode. Think about videos of Mount St. Helens. That's your explosion. And it's going to explode, and it's going to leave a pile of volcanic rock, lava rock. But it doesn't always explode. Sometimes it has lava flows. And so sometimes some lava will force its way up and run down the side. And then it'll explode again. And all that material will settle down on the side. And then we'll get another layer of lava. And then another explosion. You see what we're doing here? It's hard to draw upside down. What we're doing is we're creating alternating layers of lava and what we call tephra. I'm going to write that down here. Alternating layers of lava, we know how to spell that, and tephra, T-E-P-H-R-A, tephra, alternating layers of lava and tephra. And something that I hope that you can see in this diagram is this volcano isn't as wide. It's not as wide, but it builds up taller. It builds into a cone shape. And there's two different names that we give to these volcanoes. Composite cone. Composite, meaning it has two different things. Layers of lava and tephra. It's a composite combination of the lava and the tephra. It's also sometimes called a stratovolcano. Strato. Strato means layers. Layers of lava and tephra. Tephra, what is tephra? Tephra it's just broken pieces of volcanic rock. Broken pieces of volcanic rock. It could be ash, which is as fine as flour in your kitchen. It could be sand-sized. It could be boulder-sized. It could be as big as your car or your house. But tephra is just broken up volcanic rock. Broken volcanic rock. alternating layers of ash and tephra make up our composite cone or stratovolcano. And these are going to be your a continental arc volcano system is going to be made up of composite cone volcanoes. So where are you going to find these things? Mount Rainier, Mount St. Helens, Mount Bachelor, all of the Cascades, all the way down to Mount Shasta, up into Canada. There are composite cone volcanoes in Alaska, the Andes, and I suppose we should add this to our diagrams. I'm going back to my shield volcano diagram here real quick. If we cut off the heat, we turn off the heat. If we turn off the heat, what's that magma chamber going to turn into? What's this rock going to turn into if we turn off the heat? We got to go back to, can't pick it up. Oh, come on. You gotta be kidding me. Go back to this diagram. If we turn off the heat with our 45% silica magma, it's gonna cool slowly and form big chunky minerals, and it's gonna turn into a gabbro. Up here, these layers of lava rock, what's that? That is basalt. Basalt and gabbro, they are identical. It is the same magma. It is the same melted oceanic crust cooling into a rock. The only difference between our basalt and our gabbro is that the gabbro cooled slowly, and so the minerals grew big. Whereas our basalt cooled quickly, and the minerals did not grow very large. And in fact, some basalt, and I'll see if I can do this without knocking over my, nope, can't do it. I'm holding up my iPad here with a piece of obsidian, volcanic glass. And that cooled so quickly that no minerals had time to form. Okay, so basalt and gabbro for our 45%, for our shield volcano. Intermediate lava, intermediate magma, 60% silica, forms composite cone volcanoes. What are our rock types here? You should be able to fill them in, you know. Down below, we got diorite. Up above, we have andesite. Diorite and andesite. Let's pause before we move on to our felsic 75% silica. And let's get a little idea here. Why do we have no explosion here and explosions here? You say, Jermon, that's easy. There's this low viscosity magma and it flows. And that's true. But the part of the story that we really need to understand and that really explains all of this is it isn't just lava, it isn't just magma that's coming up when a volcano erupts. It's not just magma, there's something else. And maybe if you can imagine, if you've ever seen pictures or videos of a Hawaiian volcano eruption, there's little bits and pieces that come flying up out of these lava pools. And the reason for that is that there's gas that comes up out of these magma chambers as well. These underground cartoonish rooms that we've drawn, these rooms full of melted rock, are also full of gas. Sulfur dioxide, carbon dioxide. There's plenty of other gases, but those gases are far less dense than the magma that contains them. And so the thing to think about is bottle of soda pop. When you unscrew the lid of a bottle of soda pop, what happens? All the gas rushes to the top, right? And if you shook it up a little bit, that gas is under pressure and it all comes out the top. Same thing's happening here. With our mafic low viscosity 45% silica magma, it's so runny that that gas can just bubble up to the top. I'll just draw some little gas bubbles coming out the top. Gas is escaping freely from this magma. It is not trapped. And so we'll write that here. No trapped gas. No trapped gases. It's almost like I need a couple different colors of Sharpie for this. There's no trapped gases in this magma chamber because they all escape out the top and they bubble safely out into the atmosphere. That's why we can go eat our lunch right next to a river of lava. It's never going to explode on us. Well, what's going on here? Now, instead of those bubbles of gas, we've still got bubbles of gas down here. As a matter of fact, since they're not escaping safely up into the atmosphere, I'm going to draw some gas bubbles in my magma chamber here. Draw some gas bubbles. I added some gas bubbles in here. And some of that gas is staying down in here in this magma chamber for hundreds of years. These things, on average, every 100, 200, 500,000 years is about the schedule that these volcanoes explode. So why do they explode? They get enough gas trapped in there that that's what triggers the explosion. So we have, pardon me, we have some trapped gas. Some, not all of it. Why not all of it? Well, sometimes you get lava flows. Sometimes you get these andesite lava flows and some gas is going to come bubbling out. It's a little pressure release. Some andesite lava, some gas. But if we get, if this kind of hardens up like a little bit of a plug here, then we start trapping some gas. We get enough, and that plug is going to rupture and maybe we'll get an explosion. All right. So we've done composite cones. We've done shield volcanoes. Just one thing left to do. What do we have when we have our felsic magma? Felsic. 75% silica. Well, we already know that is melted continental crust. All right, one more diagram. We're going to start it exactly the same. Flat ground, cross section, cartoony magma chamber, 75% silica. All right, let's do it. Here's all we need to add to this diagram. We're going to make a plug, a total plug, a cork in a champagne bottle. It is a cork. Nothing goes in, nothing comes out. What's that made out of? Rhyolite. This is a rhyolite plug. Isn't that weird? That the biggest volcanoes in the world, the scariest volcanoes in the world, don't even make a mountain. That rhyolite plug right there is going to completely seal off this magma chamber from the outside world. So what's going to happen? Well, we've still got gas in there. We've got lots of gas in there. Lots of gas in there. Complete and total trapping of all of the gas that's coming up with this melted continental crust trapped in this magma that's got the thickness of toothpaste. Doesn't flow. Can you imagine carbonated toothpaste? It's kind of weird, right? But yeah, carbonated toothpaste. These bubbles of gas aren't going to bubble out of the toothpaste. They're stuck in there. That's what we've got here, is we've got carbonated toothpaste on an epic scale, and we've got a tube of carbonated toothpaste, and we're going to start shaking it up like you shake up a can of soda. Well, you probably don't, but if you did, you know what happens when you open it. Well, let's shake our tube of carbonated toothpaste for 100,000 years, 200,000 years, and our gas is going to build up pressure, it's going to build up pressure, it's going to build up pressure, it's going to build up pressure, and our rhyolite plug here is going to keep all of it trapped down here in the magma chamber. All gas are trapped. Okay, so now what? Well, eventually, we're going to reach some critical amount of pressure where that rhyolite plug just can't hold anymore. And it's going to fail. It's going to fail catastrophically. But there's no mountain to erupt, is there? So what we're going to be left with is a crater called a caldera. It's 30 miles across. Caldera, 30 miles across. It's going to blast a crater into the ground, and all of this material, everything in this crater, is going to get pulverized and vaporized and exploded, and anything within 100 miles of this is dead. Humans, plants, trees, bugs, doesn't matter. If you're in a 100-mile radius of this thing, you're toast. So what does it create? It creates, because it vaporizes all this stuff, it doesn't form a bunch of rhyolite. No, it doesn't form rhyolite. Rhyolite would be cooled magma. It's vaporizing this thing. So we've got our rhyolite plug is gone, and all of this rhyolite from around all this rhyolite, chemically, compositionally, it's rhyolite, but it's turned to ash. And this ash cloud, unlike, I'm sure it blasts a ton of stuff up in the air too, but it creates these thick ash clouds that flow along the ground. They hug the ground because they're so dense and hot. And it creates these ash flows that travel in all directions away from the caldera. Ash flows in all directions away from the caldera. They travel fast, like 50, 60 miles an hour, and there's a few different names for them. Pyroclastic flow, ash flow, and once these ash flows, once they finally lose momentum, about 100 miles away from the caldera, all of this hot, vapor hot material settles down. It's pyroclastic flow. It settles down and it turns into what's called welded tuff. Welded tuff. I need a new page for this. So our ash flow in all directions. We're going to look in map view now. We're going to look in map view. Here's our caldera. Here's our caldera, 30 miles across in map view now. Look at bird's eye view, straight down. 100 miles in all directions around our caldera, we're going to get what's called welded tuff. Welded tuff. Welded together like you weld, like a welder in a metal shop bonds, fuses metals together with high heat. We're fusing these pieces of ash and little volcanic tidbits together into a rock called a welded tuff. And these welded tuffs are kind of the fingerprint of a supervolcano. They're the fingerprint of what's left behind. You get this 30-mile across crater with 100 miles of welded tuff in every direction from it. So unlike our composite cones or our shield volcanoes, it's a collapse. The whole roof of this thing caves in. The whole roof of this thing caves down in when it erupts, and you get these ash flows in all directions. That's a super volcano, they're called. That's not a scientific term. There are geologists out there who hate the term super volcano, but it's kind of sexy and it's what they use on the news. Super volcano. Sticking with what we talked about, if we cut off the heat source to this, what's it going to be? It's going to be granite. And rhyolite plug. Rhyolite is our erupted volcanic version of a 75% magma. Let's see, couple more. I should write these down for you. Pyroclastic flow is what comes before a welded tuff. A pyroclastic flow settles down and turns into a welded tuff. Pyroclastic flow. And remember, pyroclastic flows travel, it's a low cloud of ash and gas. I just wrote gas with 2 S's, I don't know why. I hate misspelling stuff. It is a low cloud of ash and gas. It hugs the ground and it travels fast. Like, it's hot and travels very quickly. Say 60 miles per hour. So there's your bird's eye view diagram of a welded tuff. Now, like I said, Yellowstone hasn't erupted in 640,000 years. We talked about that a little bit in the Hotspots lecture not too long ago. And Yellowstone erupts on average about every 600,000 years, the Yellowstone hotspot. Is that the only supervolcano in the world? Absolutely not. When's the most recent supervolcano eruption, you might ask? It was about 26,500 years ago. It was in New Zealand. 26,500 years ago. And before that, The most recent before that was about 70,000 years ago in Indonesia. Had to check my notes. But there are known supervolcanoes, I put emphasis on that word, known supervolcanoes are New Zealand. We know of one in Argentina, Bolivia, Canada. There's a fairly ancient one in Utah, Chile, in South America. But there's probably lots of them that we don't know about yet. Geologists are still, because they don't erupt so often, there could be supervolcano calderas that are millions, tens, hundreds of millions of years old, and those calderas have all had time to fill in with other rocks, with other material, get buried. And so they're not obvious at the surface, and so there's other geophysical methods to find structures like that in the earth. But this is still a developing science, and we don't know everything that there is to know about these supervolcanoes because, like I said, we've never observed any of them erupting. But we can probably be glad for that. Anyways, that's about all I got for you on the three styles of volcanism, the three styles of volcanoes, that relate perfectly to our three types of magma, which relates perfectly to the amount of silica in the magma, and relates perfectly to the setting on the Earth where it is. 45% silica ocean floor, 75% silica middle of the continent, 60% silica somewhere at the margin of a continent. We've got a couple of exceptions, just a couple of exceptions that I want to talk about briefly, sort of as a teaser to some of what's coming up ahead. We're not going to go into it today, but are there exceptions to this rule? Yes. Are you ever going to find 75% silica magma coming up out of the ocean floor? No, you're not. That's continental crust, and it's only going to be found in the continents. But there are many examples around the world of 45% silica magma, lava, found in continental settings. And right here in eastern Washington is a prime example. The Columbia River basalt is an ocean rock. That's what the ocean floor is made of. But here we are in eastern Washington with layers upon layers of basalt lava rock. There's also a huge flood basalt province, which is basically a shield volcano on the continent in India. And there's a flood basalt province in Africa and also in Brazil. I think it's Brazil, somewhere in South America. So we have other, we have exceptions to this rule, and we will go into that in great detail in future lectures. Today's purpose was really just to get the basics to these three types of volcanoes and how they relate to the three types of magma that feed them. That's it from Ellensburg for today. I hope you guys have a wonderful day. Stay safe, stay healthy, wash your hands, and we'll see you next time.